With Chapter 2, we're going to be moving into a much more abstract and symbolic branch of math than we saw in Chapter 1, where we're looking at things called sets. We're looking at some very basic ideas of a branch of math called set theory, where, broadly speaking, a set is just a collection of things, where we call those things elements or members, depending on exactly how we want to handle the notation. And for mathematicians, it's very, very important to be able to do things like this, to be able to very clearly state, hey, here are the things that for this problem I'm concerned with, here are the things for that problem that are of note, to just be able to collect all the things that in a given context matter and describe them in a careful and exacting way. That's the nature, that's the necessity of sets and set theory, where when we're talking about this idea, the idea of a set, we do want our set to have a property that it is said to be well defined. That is, we have a clear and obvious way through which we can reference it and what it is meant to do. That is, what the set is and what it is meant to describe. The collection of objects, the collection of elements that are relevant to it, that fit within it. That's our idea, where we can represent a set in terms of a word description, roster notation, or what is called set builder notation. So, like I said, a set can be just about anything. In terms of more mathematical and abstract ideas, like I said, we're sort of hinting at, we would talk about sets of numbers, most naturally, like the set of the odd numbers, for example. But to help get our feet set here first, I'm going to start with a looser and less numerical example where I am going to say that the set M is the set of months. I keep saying months. Months in the Gregorian calendar. And that word there, Gregorian, might throw you off in terms of what I'm talking about there, but what I'm referring to with the Gregorian calendar isn't actually anything all that special. It's just January, February, March, April, May, June, July, August, September, October, November, December. It's the calendar that we follow in the Western world and most of the most of the rest of the world at this point in time. Although, for the purposes of future proofing, I must say that maybe we'll move on to something else eventually. Who knows? I personally like the idea of a 10-month calendar, but hey, that's just me. Anyway, this is what we'd be talking about with a word description. We have our set M. We describe it in a sentence. That's what a word description is. Sometimes with math, we have to give things really specific and almost unnecessarily picky names just to be sure that we have that clear definition. This is one of those ones where you know precisely what a word description is once you see it. The name itself makes it sound more obscure than it really has to be. But that's what we're talking about. A word description is just a description in terms of words, sentence. Although a word description is not always going to easily fit. Like I said, in this case, we're dealing with something that's a bit looser, so it fits really well, but with other things, it might not be quite so nice. Where from there, we could talk about this as well in terms of roster notation. So if I say M is equal to, then what I'm saying here is that M is going to be some collection of things, or if I want to use roster notation, I open up the set using what's called a curly brace. And the easiest way I've always heard to draw a curly brace is to start like you're going to try and draw a 5, and then turn it into a 2 at the bottom. It's kind of cute, it usually works. But anyway, we call that curly brace, that's how we're saying the set is starting, and then we put the things in there. So I'm going to be using abbreviations here to save some space. We'd have January, February, March, I think April is APR, but I can't remember, May, June, and I'm just going to put some dots there at the end because I still ran out of space, and then we close off the curly brace, where roster notation means representing the set as a roster. So if you want to talk about like the roster of the basketball team, you could do it in exactly the same way. You just list off all the player names, where to be mathy about it, you throw an equality and a curly brace in there. Curly braces are specifically used for references to set theory and really nothing else. Well, not nothing, but this is the main place where it's used. So that is roster notation. Roster is just a list. It's just a roster. It takes all of the objects in there, which fits really well for something like this, despite the lack of space, because there's only 12 months. So it's very easy to list everything. But much like how a word description might not very well fit certain kinds of sets, especially obscure sets of numbers, roster notation also has some limitations for the fact that there are cases where you want to be able to list everything, and everything is much more than 12. We're going to talk about it later with ideas of infinite sets, but if you wanted to describe every single thing in an infinite group of things, you'd run out of time before the set does. And this is the sort of problem that people ran into when they were first defining the idea of set theory, where, again, talking about things in terms of collections, that's pretty ancient because its necessity should make sense in a mathematical context to be able to specifically describe things, but the specific idea here comes from the paper on a property of the collection of all real algebraic numbers by George Cantor in 1874, where it was actually a very controversial paper in its time because there were a lot of people who had this very rigid idea about how math should work. These were people that are known now as mathematical constructivists, who thought that if you're going to give an example of something, you have to actually give an example of it. You can't just talk about it sort of in reverse, in a sense, and that's what people thought Cantor was doing, and it took a while for people to warm up to the ideas that he had, but eventually this did get accepted and brought into the mainstream of math, as it were, although what's mainstream for math is still pretty obscure for most people, but this is a math class. I reserve the right to ignore the fact that most people think math is weird and irrelevant. This is my time. You're supposed to listen to me. Anyway, that stuff did take a little while to catch on, and all of the weird details in here, it does go in some strange directions, where you can get some odd paradoxes in here, like Russell's paradox, which asks us to consider the elements in a set of all sets that are not members of themselves. And trying to describe that thing as anything other than a word description is a little weird, because you get all the things that are not things. It makes your head hurt. It's part of why it's so popular to think that Cantor went crazy trying to describe infinite sets. Point is that this goes in weird directions. It's not always easy to get something nice where you can describe all the things all at once. So our third bit here is maybe not the one that you'll see the most, but it is the one that's most natural for this. And if you go far with math, if you work with a lot of math, it's the one you'll probably get the most often, which is set builder notation, where it's set up in very much the same way as roster notation. You say your set of things M, that's the name there, is equal to something inside of a curly brace. Remember, curly braces here are telling us we're doing set flavored things. And then you take some element in there. So I'm going to use small m. Usually the way that set notation runs, you reserve capital letters for the full set, and you use small letters to describe the thing inside of it. So big M, all the months, little m is a month, or a thing in the collection of months. I don't know for sure yet, but small m. Where then you draw a vertical bar. And what the vertical bar here says is something like such that. It is the things following a given rule, where the rule is what we put after that. So the rule here would be something like M is a month. So set builder notation, that's what we're looking at here, is talking about building the set in terms of a rule. Now, often, especially with something like this, that rule ends up looking a lot like the word description, but in other contexts, in more specific mathematical numerical contexts, they do have a bit more of a distinction there. In this case, it just happens that because we're describing months, the rule is months, so that's that. But point is, got our big thing, curly brace, single thing that should be in there, such that thing happens. That's how we use set builder notation. And usually I'm not too picky about notational details here, but in this case it is actually very, very important that you follow these ideas to the letter. The point here is to set up the way that we describe things, so it's very important that you describe them in that way. Although I will mention that in some contexts, instead of using a vertical bar there, they use a colon. It's the vertical bar in this class. No really good reason. Never been able to get an explanation for why people like that instead of the colon, but that's what we'll use here. So for another quick example we can have here to just keep wrapping our minds around that, we can talk about the days of the week, where we have the set W with the curly brace X, so X is a thing in there, vertical bar, such that X is a day in the week. The exact same sort of idea. We're just talking about collections of things. That's what we're looking at here. So let's take one more quick example here in terms of how, actually not one more, a couple more quick examples here in terms of how this works in practice.